So it turns out that there's a relationship between determinants and row operations, which of course we represent by elementary matrices. Now I say that this is surprising. It's surprising because when we were talking about row operations, row reductions, elementary matrices, etc., there was no discussion of determinants. And furthermore, once we have started talking about determinants, there was no discussion about anything having to do with row reductions. So they have been entirely separate conversations. So not immediately clear that there should be any connection between them at all. That being said, turns out we already know how determinant is affected by 2 of the 3 different kinds of row operations. We haven't said this in this language exactly yet, but this is true. Now we're going to ignore this side of the table here for a moment. We'll come back to that in a few minutes. But we already know what happens when you do this row operation to a matrix, what the resulting effect on the determinant is. If you switch 2 rows of a matrix, the determinant gets multiplied by -1. That's our anti-symmetry property. And we already know what happens when you multiply a row by a non-zero scalar. From multilinearity, we know that when you multiply a row by a non-zero scalar, it doesn't even need to be non-zero. The point is by multilinearity, the determinant gets multiplied by that same constant. So this we already know. What we don't yet know, or at least what we haven't thought through yet, is what happens when you do this row operation, when you add a multiple of one row to another row. And is there a nice, of course you can see the answer here, but is there a nice way to think about how it is that we would conclude, what happens to the determinant when we do that? So we're going to look at this calculation up here. Here's the matrix that you get when you add a multiple of the ith row to an existing jth row. So being as this is, we're adding to the jth row, that means that we're in the jth position here. These are going to be the jth rows that we'll be looking at. Okay. Alright, so what I'm going to do is I'm going to again apply multilinearity. Multilinearity says that if you have a linear combination in a position, in one of the vector entries of the matrix, and if you hold everything else constant and fixed, none of that's allowed to change, none of this down here is allowed to change, right? Then you can take this linear combination in this position, take this linear combination in this position and expand it to the outside. So that linear combination, you'll notice we have 1 times the vector rj, and then c times the vector ri. So multilinearity tells us that we have this relationship between these 3 determinants. Now, what are these 3 determinants, and how are they relevant to me? Well, you'll notice that this is the original matrix. This is the matrix where I have rj in the jth. I have the jth row in the jth position. So that's my original matrix A. This is, of course, by design, the result of doing the row operation in question to that matrix A. So what about this matrix? What can I say about this? Well, this is the matrix that you get when you copy the ith row into the jth row. So what that means is these 2 rows are the same. And what do we know about determinants? When 2 rows are the same, well, the determinant is equal to 0. Alright, so very nicely, what we end up with then is that this term goes away, and the determinant after that row operation is equal to the determinant before that row operation times 1. In other words, it's exactly the same determinant. So that proves this fact. So nicely, we now know for all three row operations exactly what does it do to determinant. And again, I can't emphasize enough, this is completely unexpected. We did not have row operations at all in mind when we wrote down the formula for determinant. Okay. Now, before we go on to the other side of this table, I want to show right away that there's a nice application for how to use these ideas, and that is you can use row reductions actually to compute determinants. And I'll show you by example. Here's a matrix that for which I might be interested in the determinant. Of course, we know how to compute determinants. We have this method of cofactors, but let's go ahead and do this anyway. What I'm going to do is row reduce this matrix. Just go through and do the usual process of one row operation, next row operation, etc. And each time I do a row operation, I get a new matrix until finally last operation gets me down to the reduced row echelon form. Okay. All right. Well, we know now what happens to the determinant in each one of these steps. So here, because I switched two rows, the relationship between those determinants is just that of a minus sign. So that means that this matrix has a determinant that's just the negative of the original matrix. All right, next step. This next step here, and going from there to there, I add a multiple of one row to another row. That doesn't change the determinant at all. So these two matrices have the same determinant. That is, it's still equal to the negative of the original determinant. Okay. Next operation. Now here I've multiplied one of the rows by a constant, and the rule is when you do that, you get a corresponding factor in the determinant. So here I've multiplied the third row by 1/4, and therefore I get a factor of 1/4 in the determinant compared to the previous matrix. Okay. All right, last step, actually two row operations in a row, but in both of these steps, in both these row operations, I'm adding a multiple of one row to another. It doesn't change the determinant at all. And so these two have the same determinant. That is, it's still negative 1/4 of the original determinant. Now, this by itself doesn't answer our question. The good news, though, is that this matrix is something that's easy to compute the determinant of. Its determinant is 1. It's a upper triangular matrix. Diagonal, in fact, in this case, but certainly it's an upper triangular matrix, and the product of the diagonal entries is 1. Okay. Well, that being 1, I now have a really easy little bit of algebra that I can solve to compute the determinant of the original matrix, and the determinant of the original matrix is now negative 4. So this process, the point is if you have a row reduction, you can use that row reduction, just keep track of what happens to the determinant correspondingly, and then knowing the determinant of the end matrix will allow you to sort of work back to find the determinant of the original matrix. Good news, finding the determinant of this reduced row echelon form matrix is always going to be really easy. Not hard to persuade yourself, just from the rules of reduced row echelon form, all reduced row echelon form matrices are upper triangular. In fact, it's even better than that. Keep in mind we're looking at square matrices. All reduced row echelon form matrices, not only are they upper triangular, but they're either going to be all 1s on the diagonal, if your reduced row echelon form is the identity, such as in this case, or there will be a 0 if it's not the identity matrix. If it's not the identity matrix, there will be a 0 somewhere on the diagonal, in which case the product of the diagonal entries is just 0. So reduced row echelon form matrices are super easy to compute the determinants of. They're either the identity, in which case the determinant's 1, or they're not the identity, in which case the determinant is 0. Okay. Now, you look at this process and you think, well, which would I prefer to do this whole process to compute the determinant, or would I rather just look at this matrix and do cofactors? A little cofactor expansion maybe along the, I kind of like the looks of this first column here. Look at that, I get a bunch of zeros. And that seems much more appealing at a glance. But for larger matrices, it's really not. So let me make a quick argument down here below. Let's think about what would happen if I had a little bit larger matrix. And let's say that A is a 100 by 100 matrix. Now that sounds implausible, but let me remind you, matrices can be viewed as representing systems of equations, and you might have a system of equations that involves a bunch of variables. You might have a physical system that you're dealing with where there are a lot of variables involved. It's not unusual at all to have maybe 100 or more. Okay, so let's say we have a 100 by 100 matrix, and let's count how many calculations if I use the method of cofactors. Well, if I use the method of cofactors, I would have to pick a row or column. So I would have 100 minor determinants to compute. So 199 by 99 determinants to compute. So for each one of those, I would have 98 by 98 determinants to compute. And for each of those, I would have 97 by 97 determinants to compute, etc. And you can see the pattern here. And so, in fact, I would end up with 100 factorial, approximately, order of magnitude, 100 factorial computations. This is a tremendously huge number. This is such an enormously huge number that the fastest computer known to humanity, working for the entire known lifetime of the universe, could not do this many computations. It's just absolutely intractable. Okay, so now let's consider our row reduction method, our brand new row reduction method. And let's order of magnitude, how many calculations would I have to take to do this? Well, I would have to row reduce, I would have to fix, as it were, 100 columns. We row reduce by fixing columns one at a time, left to right. For each column, I would have to fix each entry in that column, of which there are 100 entries. Each of those entries that I fix with a row operation. And of course, you have to do row operations all the way across. And so each such row operation would involve, again, order of magnitude, 100 calculations. So that's about a million. Right? Order of magnitude, we'd have about 1 million calculations to do to compute the determinant of a 100 by 100 matrix using this row reduction method. So we have what is for a computer a snap of the fingers versus what is, even for a computer, completely intractable. So this row reduction method, very efficient, very smart way to compute determinants, except in the smallest of cases, such as 3 by 3. In this 3 by 3 case, you maybe just go ahead and do cofactors. Almost any other case, absolutely use row reductions. Okay, so let's go back to our table now, and let's finish filling in this table. So we were talking about what happens when we do a certain row operation. What is the corresponding effect on determinant? Well, now let's think about these row operations and ask, what are the matrices that execute those row operations? Remember, for every row operation, there is a corresponding elementary matrix. All right. Well, here they are. There's a matrix that switches 2 rows. There's a matrix that multiplies one of the rows by number C. And here's a matrix that adds a multiple of one row to another row. Okay. And now, let's ask, what are the determinants of these matrices? And these are easy determinant calculations. In fact, there's not many row operations you would have to do to these. By definition, these are elementary matrices, and so each one can be row reduced by one row operation. And not hard to show, each of these determinants then is what these numbers. So something really seemingly coincidental has happened, and that is when you do a row operation, the effect on the determinant is multiplication by the determinant of the corresponding elementary matrix. That's a really surprising result, that these numbers here happen to be exactly the same as these numbers here. So let's say it again, a little bit faster this time. This is a recording. When you do a row operation, the effect on the determinant is multiplication by the determinant of the corresponding elementary matrix. And we can write this as a result. Here it is. When you do a row operation to a matrix, the effect on the determinant is multiplication of the original determinant by the determinant of the corresponding elementary matrix. I've said differently, for an elementary matrix E, we have this relationship here. And this is what you might call a sort of a multiplicativity. Multiplying matrices multiplies their determinants. Okay. Critically, though, all we know this is true for is elementary matrices. All right. Not hard to show, however, that the above is also true when you have a product of elementary matrices. In fact, you can prove this result just by making successive applications of the theorem that we already know. So if E is a product of elementary matrices, just apply this theorem as many times as necessary, and you get the desired result. So I'm going to leave it to students to check this result. That would be a good practice problem. Try to apply this result to prove this result. Okay. All right. This gives us a wonderful result that relates determinants to non-singular matrices. And let me just remind you before we get into that, non-singular matrices, don't forget a non-singular matrix is an invertible matrix and vice versa. And we've already made a kind of a big deal out of the fact that even though non-singularity and invertibility are completely different statements, right? I mean, non-singularity comes from thinking about how a matrix row reduces. You know, what is the reduced row echelon form? Invertibility is a statement about matrix multiplication, seemingly a different thing. So the fact that these are entirely simultaneous is already pretty surprising. And so even more surprising, we're going to find out that there is a yet another third simultaneous statement that has to do with determinants, which again, at a glance, seemingly a completely different idea. So here's the result. A matrix is non-singular, aka invertible. We already know that these are equivalent. Matrix is non-singular if and only if the determinant is not 0. Okay, wonderful little proof. Here it is. Our matrix A has a row reduction somehow or another. Right? This is how row reductions work, is that our original matrix, there is a series of row operations. Now, importantly, E here is not necessarily an elementary matrix, but it's a product of elementary matrices. And after applying the appropriate number of row operations, you get down to the reduced row echelon form. So we've seen this this algebra before, a little quick algebra representing an entire row reduction with matrix multiplication. Okay, and then using the result above, we have this. Okay, and good news, we know that the determinant of a product of elementary matrices is never 0, and we know this because we know exactly what the determinants are of elementary matrices. Come back up here and see them. Elementary matrices, their determinants are these numbers, which are not 0, not 0, and not 0. So importantly, elementary matrices determinants are never 0, and therefore likewise a product of elementary matrices, the determinant is never 0. Okay. All right. So let's think through now the statement in question. We know that a matrix is non-singular if and only if the reduced row echelon form is the identity. And we previously observed that the reduced row echelon form is the identity if and only if the determinant of that reduced row echelon form is non-zero. We made this observation that when you get a reduced row echelon form matrix, it's either the identity matrix, in which case the determinant is 1, or it's not the identity matrix. There's a 0 on the diagonal, and the determinant is 0. So it's the identity if and only if the determinant is non-zero. And from this equation, and again, using the fact that this determinant is never 0, the determinant of R is non-zero if and only if the determinant of A is non-zero. That proves our result.